Another important part of the control plane is going to be that protocol we just mentioned, the Overlay Management Protocol. OMP is really interesting. We just mentioned that it's a protocol that isn't just designed to carry routes. We can carry routes, that's one thing we can carry, but we can also carry things like attributes. And we can carry things like pieces of information, such as TLOCs. And other things, lots and lots of other types of information. This is known as an extensible protocol. It's a very fancy word, and it basically means that it's extremely flexible. We can add to it, we can include things in it that maybe the creators of the protocol didn't originally have in mind. And this should remind us of another protocol, which is BGP. Now, BGP, just like OMP, is an information carrying protocol. I don't personally like calling this a routing protocol because it's information carrying. It doesn't just carry routes. For example, BGP can carry IPv4, and it can carry IPv6, and it can carry, for that matter, multicast routes and MAC address information. It can carry whatever we want because it's an extensible, flexible type of protocol. When we look at OSPF version 2, this was IPv4 only, to the point that if we wanted to carry IPv6 routes, we've got to run a different protocol, OSPF version 3, which is designed to run IPv6. So we didn't want this static world. Instead, the creators of this particular architecture saw fit to deploy a protocol that's much more like BGP. Now, why didn't they just use BGP? Well, because they had a few things that BGP wasn't actually able to do for them, and so they just thought, hey, rather than use BGP and be limited by the things they wanted to do, they just created their own protocol. As if they just were going down to the local store and buying a loaf of bread. They just went down to the local store and bought themselves or made themselves a protocol. So that's a pretty cool story. So the way that OMP works is going to, again, continuously remind us of how BGP works. For example, when I'm looking at, let's say, an edge node forming a OMP adjacency or peering with a controller, well, at this point, this is going to be a TCP connection. Why is that so important? Well, because we're not using multicast, which is a local concept, which again is what OSPF and EIGRP rely on. They want to find attached network or attached neighbors or adjacencies, not physically attached, but attached to the same subnet from a layer 3 perspective. So we use multicast, just a local multicast communication in order to find our neighbors. We can't do that because we might have lots of underlay routers along the path here. And so physically we might have to pass through a bunch of different routers, but we know that there's this capability for us to form a, let's say it's a TLS connection between the two, and now I can use TCP to form a connection across it. So that's the idea of forming TCP peerings and why it's so important that we're able to do so. Furthermore, we might say, okay, cool, so then if I have another edge device down here, I would form an OMP peering, right? Well, that's actually not how it works. We want to scale this out, and so if I have another edge device down here, I will form an OMP peering with my controller, but I will not form one with other edge devices. So if I'm going to share, let's say, subnet information, well, I'm going to have to share it, change colors here, I'm going to have to share that information with the controller, and the controller will reflect that information, so to speak, and send it down to all of the other edge devices that are in my network. This should also feel a little familiar from a BGP perspective because this turns the controller into effectively a route reflector. BGP requires, on some level, that we have a full peering of peerings, a full mesh, rather, of peerings. There we go. And so we can get around that requirement by configuring route reflectors, which allow for these more centralized devices to be the only ones that form relationships with the edge devices. And so that's the exact architecture we're going to replicate here with OMP. The beautiful thing about this is that this helps us out with scaling, especially for those very large networks with hundreds or thousands of edge devices, we don't have to worry about a full mesh of OMP communications and peerings among all of the edge devices. They just don't actually form peerings with one another. They only form peerings with the controllers or the vSmarts. So what exactly are they propagating? We keep mentioning it's information, and that's great, but what type of information are we actually propagating here? Well, there are going to be 3 different route types that are handled by OMP. The first of which is known simply as an OMP route. Pretty straightforward. An OMP route is all about carrying our subnets. So we're going to want to advertise again subnet A here, so that subnet A and subnet B in the bottom left, that they can reach one another. Now, how do they reach one another? Again, we're going to form an IPsec tunnel here, and we're just going to throw our traffic across the IPsec tunnel. But notice that the data plane path is very different than the control plane path in this case. In many networks, we would expect that the control plane and the data plane kind of run against one another, where I advertise a route to you via the control plane, I advertise that route down, and the data plane goes up against the flow of that control plane information. Well, that's not technically the case here, because I didn't tell you where subnet A was, nor did you tell me where subnet B was. Instead, it's the controller that told us via out-of-band communications. And that's what's so fascinating about this architecture is, again, we are hearing these routes, these OMP routes from the controller, and they let us know where all of the subnets are in the environment. Now, it is worth pausing for a moment and noting that OMP, this is SD-WAN only. We're not running this in our networks. We're not suggesting anybody replace GRP or OSPF with OMP. That wouldn't make any sense. It's also Cisco proprietary. We're not going to expect that every SD-WAN provider is running OMP. Other providers and other architectures will be using different solutions. So here's the question now. We tend to draw things like this where subnet A is attached from a layer 3 perspective to the edge device. What if it's not directly attached? What if we have something like this, where I'm connecting down to, let's say, a layer 3 switch, and this layer 3 switch maybe has a bunch of other layer 3 switches, but even if it's just a layer 3 switch connection, at this point we might have lots of subnets. We might have subnet A as well as subnet D attached here. So how does the edge know where subnets A and D are? Well, the edge is capable of running these different protocols. It can run EIGRP. It can run OSPF, or BGP for that matter. We can run these different local routing protocols. We could even run static or, and obviously connected routes, but we have a choice over how to run internally to the rest of the network. Again, I'm not running OMP internally. I am only running OMP to the controller, so that I can learn where all of these networks are. So how do I know where all these networks are that I'm advertising to the controller? Probably via internal routing protocols. So just wanted to pause the OMP conversation to make sure we understand, how does this edge device know where all of the downstream subnets are if they're not locally attached? So at this point, we see that we're sharing OMP routes. Now I know where subnet A is and subnet D lives, and the top edge knows where subnet B lives. So that's cool. So we know where these are, and so we can actually send across the IPsec tunnel to one another in order to enable traffic flow from a data plane perspective. So the OMP route is going to help us out with that. The other one, which we've already mentioned, is going to be the TLOC route. The TLOC route is going to let me know how to reach a TLOC, because that's not actually part of the TLOC itself. Now, why don't we just embed that into the TLOC? Well, because this information could change. This could be dynamic, and so, which is why it's part of a dynamic routing protocol like OMP. And so we want the TLOC, this, to be static. For the most part, our TLOC information isn't going to change. Think about that 3-tuple. The system IP should never change. The connection, the WAN connection point, that should never change either, because if I create a new WAN link or get rid of a WAN link, that kind of scraps the TLOC altogether, and neither should the IPsec versus GRE ever change. This is intended to be very static. Meanwhile, how I connect to the TLOC via this IP address or this IP address or this IP address, well, that could change over the course of time. Maybe my WAN service provider provides me with a new IP address for one reason or another, or I put it behind a router and now it's got a completely different IP address for connectivity. So the TLOC route is going to dynamically update my edge devices with information on how to connect to remote TLOCs. So that's the purpose of that route. And then lastly, the third one is known as a service route. The service route gets into more interesting elements of the software-defined nature of SD-WAN. It's going to allow for things such as service chaining. Service chaining is when I want to, let's say, take a packet that comes into a router and it's destined for subnet A. Maybe I say, it's great that you're destined for subnet A, but I want to send that traffic through a firewall first. And so I send it to the firewall and I use encapsulation in order to accomplish that. So that's all we'll say about service chaining for now, but it is an important part of software-defined networks to be able to do things like that, and the service routes will help us get there. Now, one last aspect of OMP is that OMP is also going to be responsible for our policy enforcement. This is important because when we think about SD-WAN, one of the advantages of SD-WAN is getting onto that manager, creating policy in a single place. I might want certain traffic types to take certain WAN links. So how do I enforce that? How do I tell an edge that, hey, that's great and all, but now this is voice over IP traffic coming in and I want that traffic to go a different way? Well, the way I do that is via policy enforcement thanks to OMP. OMP can control different routes, and by doing so, it results in the policy that I'm trying to deploy. So this is one of these, we use this fancy word called abstraction. The idea here is that me as the network engineer, usually I have to directly create the configuration for something like this. And this gets very, very complicated, especially for large networks. But abstraction says rather than it being a direct relationship here, now I as the admin, I create the policy, and the policy is going to be what performs the configuration thanks to my manager. So I create the policy in the manager performs the configuration using all of the APIs that we've talked about, usually pushing it down via OMP or possibly via netconf or something like that. But in the end, what we're talking about here is the fact that I as the admin get to create the policies, and that policy does get enforced thanks to my OMP, the way that I'm distributing my routes.
Thanks for watching. Be sure to click here to subscribe to CBT Nuggets and click the notification bell to make sure that you're aware of every time we post new content. If you're interested in a career in IT or you want to brush up on your IT skills, then swing over to our website, and while you're there, be sure to sign up for a free trial.